This lesson is about quantum numbers, and the challenge with quantum numbers isn't so much how to do it, but what makes it difficult is visualizing what we're doing and why we're doing it. Well, our ultimate goal is to assign every electron in the atom a home. In essence, we're giving them an address, kind of like if you give your address to the post office. We need to be able to find you as approximately and as quickly as possible. We're going to get to that in a moment, but I want to start with this visualization here. We've just got through learning that the electron cloud is broken up into rings, like the Bohr model says. Now get that idea of a two-dimensional ring out of your head, and we have to go to 3 dimensions. Because in reality, they're not just rings, they're shells. And this analogy of an upside-down office building kind of helps, or it can help if you can wrap your brain around it. The idea of how this shell model is filled with electrons. So let's start with this upside-down office building, and let's call this building Electron Cloud. That's the name of the official building. The first floor of this building is kind of small. There's not a lot of room on the first floor to do much. So maybe this is just a lobby with a single desk. That's about all it has room for. So the first floor of this building, pretty simple, not much room to have stuff going on. Well, on every floor, if you've ever been in a real office building, every floor kind of opens up into a lobby. So there is a lobby with a receptionist on every floor of the building. Now the second floor, since it's a little higher up, is bigger. And because it's bigger, we have a little extra room, and we're going to let this room be for offices. And every floor is going to have room for more offices. Now, not every office is created equally. Some offices are designed differently. These offices, we could say, are maybe divided up for the big bosses on each floor, the managers. And then maybe this office here, this would be for your peon engineers. And in every one of these, we can throw a cubicle. So maybe teams work in these little mini offices. And then every floor would have the same. And then maybe this one's broken up for even smaller groups. Maybe tech people or telecommunications people. But the bottom line is, as the electron cloud gets bigger, as the office building gets bigger, we can divide each floor more and more, and then we can take those subdivisions and divide those more and more. But ultimately, in every place, we have to have a station. We have to have a place to assign people. And that's eventually what we will do for the electron. So the moral of this story is just keep this model, this idea in your head as we go along. And I'll refer back to it every once in a while just to kind of help you conceptualize what we're doing. So every electron has 4 unique quantum numbers to describe where it is. The first one is the principal quantum number. The second one is called the angular momentum quantum number. The third one is the magnetic quantum number. And the last one is called spin quantum number. Now, I mentioned earlier there's an analogy with assigning an electron an address. And so let's take just a quick look at that and how we can actually be assigning an address. Well, let's say you want to mail a letter, someone wants to mail a letter to you, and they want to know where you are. Where does it go? Well, probably the vaguest reference is to tell you what state you're in. If you say I'm from Texas, that narrows it down. They have a better idea about where you are, but it's not very accurate. This is analogous to the principal quantum number, which is the ring. Then if you want to get a little bit more specific, you can say what city you are. I'm in Dallas, I'm in Houston, I'm in San Antonio. That's better information, it's more specific, we have a better idea of where you are, but not perfect. Let's get even more specific, and now we can tell what street. Well, now I've got it narrowed down pretty well. If I get it to the proper street, I have a better probability of finding you with this letter. And then finally, to get it right to you, I need to know your house number. With a house number, I have a high probability, maybe 90+% probability of my letter finding you. This is what we're doing with the electron. Every one of these quantum numbers that we assign gives us more and more specific indication of where the electron might be. The next important piece of information is what we call the Pauli exclusion principle. Pauli recognized that no two electrons can have the same set of 4 quantum numbers. Well, that makes sense. If you have an address, you have a home, you can't have 2 houses with the same exact house number on the same street, in the same city, in the same state. Can't occupy the same space. So electrons have a similar principle that we need to go by. Let's talk about what each quantum number means. First of all, we have the principal quantum number, which is symbolized by the letter N, and it indicates the shell, the energy level, the ring on which the electron is located. So there are numerous rings in any atom. They're all always there, even if they're not occupied, they're always potentially there. We start labeling them as 1, 2, 3, 4, and so on. So the principal quantum number is a very simple concept. The number of electrons that can fit in a shell is found by this little simple equation, 2n squared. So on the first ring, plug in a 1. There can be 1 squared, 1 times 2, or 2 electrons. On the fourth ring, 4 squared is 16, times 2 is 32, so 32 electrons can fit on the fourth shell. The second quantum number is called the angular momentum quantum number. This quantum number identifies sublevel or subshells. So this would be the type of subdivisions on each floor of our office building. There are 4 main types. You see in the picture here, there is an s orbital, or an s sublevel, that's more correct, s sublevel. There is a p sublevel and d sublevel. There's also an f that you're going to see quite a lot of. So what this quantum number does is talk about the shape of the sublevel, the shape of it. It is given by the letter L, and L is going to have some numerical values, and we're going to associate these numerical values with particular sublevels. So when L equals 0, we're going to know that's an S sublevel. When L equals 2, we're going to know that's a D sublevel that we're talking about. So this is the second quantum number, L, angular momentum. This gives us sublevels, S, P, D, and F. The third quantum number is called the magnetic quantum number, and this one gives us the position of the subshells. And once we know this quantum number, they are now, these spots, these locations in three-dimensional space are called orbitals. So you have to have 3 quantum numbers assigned, that's N, L, and this one, to identify an orbital. The symbol for this quantum number is M sub L, because it depends on what the value of L is, and it denotes, like I said, the orientation, the position. And what an orbital is, let's go ahead and define what an orbital is. It is a region where you have 90% probability of finding an electron in the cloud. So that's kind of like having your street and an address. Once I get there, I have a pretty good chance of finding you. And that's as good as we can get, really, with the electron. You may want to print this slide, and if you haven't already printed this out, just to have it in front of you as I go through assigning the numbers in a moment. Then the last quantum number is called the spin quantum number. Once we get this specific, we're talking about an individual electron and what it's doing inside the orbital. There are only two values for electron spin, plus 1/2 and minus 1/2. And it's perfectly fine just to imagine an electron spinning, one spinning clockwise, the other spinning counterclockwise. They just have to have this property of oppositeness so that these two negative particles can occupy the same region, this orbital. If not, since they're negative, they would fly away from each other. But since they do this oppositeness, they are allowed to live in the same room, so to speak. So looking at what the implications are for this, here is the idea of what the S orbital looks like. It's roundish, spherical shaped, but in between you have these nodes, and in these node regions, electrons cannot exist. Almost zero probability of finding an electron here. You can have an electron inside 1, 2, 3, but not in the middle. Very similar to Bohr's model of the atom. We visualize the S orbital, kind of a round ball. But then we have a p orbital, and the p orbital is made up of two lobes, as you see. They're dumbbell shaped. And because there's two of them, we can align them linearly. So you go back to math class and you think about lines. In three-dimensional work here, we can line these up along each of the three axes, x, y, and z, so I can take this sublevel, the p sublevel, and I can spin it three different ways, and we call it a px orbital, py orbital, pz orbital. And the only difference is the direction they're pointing. They're all the same energy, they can all hold the same amount of electrons, they're just pointed different directions. The d orbitals are really wacky looking. Now we have these four things, these four three-dimensional objects. It's very hard to line them up. So instead of linear, they're lined up planar. And you can see from the xy, the yz, and the zx how they line up on the xyz planes, if you break it all up. And then you have two that are a little weird. You have the x squared minus y squared alignment, and then you have the torus here, the dz squared orbital. And then you have the f's. I'm not even going to pretend I understand all the math behind the f orbitals, but as you can see, the more subshells you have, the more orientations of those subshells you can have, so the more orbitals you can have. Past F, we began going in alphabetical order, and there is such a thing as a G subshell and G orbitals, and then there is an H subshell with H orbitals, and it goes on and on and on. It's just that on the periodic table, no element has above an F in the ground state, so that we're only going to learn about S, P, D, and to some extent F. Now, what's hard to conceptualize is that all of these subshells and orbitals come together on each ring, on each principal level, and they form almost a completely spherical shape. So I want you to go to this link right now on the PowerPoint that I have attached in Power School, or our school town, sorry. Click on it and watch it. I think you need to see this and see how they all come together before we get too much further. Okay, I hope you're looking at that page I asked you to print out and have next to you. We're going to assign some quantum numbers And I want you to keep in mind, these numbers don't really mean anything. They just represent solutions, or the number of possible solutions to Schrodinger's wave equation. So remember, we have N, L, M sub L, and M sub S. That's principal, angular momentum, magnetic, and the spin quantum number. So we start out, N can only equal the integers 1, 2, 3, 4, and so on. There is no 0 for N. You start at ring 1. Then L can only equal the integers 0 up to N minus 1. And then M sub L, N sub L can be for any value of L, negative L up to positive L. And then we're going to pretty much ignore the spin quantum number because I've already told you that it's going to either be 1/2 or negative 1/2. So we're just going to kind of put it to the back right now. We'll get it later. So let's go through and let's assign specific quantum numbers. Let's start when N equals 1. Well, if N equals 1, then L, if you come up here, L is 0. And then we go next would be 1. But for this one, if N minus 1, 1 minus 1 is 0. So that's the only quantum number we have when N equals 1. Just 0. And then M sub L, if L is 0, then there is no minus and positive 0, so M can only be 0. All right, before I say much else, I'm going to come over here, and I'm going to do N equals 2. All right, so on the second ring, if N equals 2, L can be 0, N minus 1 is 1, so it can also be 1. Then M sub L, we have an M sub L for 0 of 0. And then for L equals 1, the M values can be negative 1, 0, and positive 1. Again, these numbers don't mean anything. They just represent the numbers of solutions, and these relate to levels, sublevels, and orbitals. So let's go back and let's kind of fill in that. Okay, so for N equals 1, this is the first ring, or the first shell. On the first shell, L equals 0 tells me that there is one subshell. Again, think back to our apartment building analogy. One subshell on the first floor. We call the first one the S. If you remember back to our atomic spectra, we talked about when we looked at those lines, we had sharp, principal, diffuse, and fundamental lines. This is where S comes from. Not spherical, but sharp lines. And then finally, we have on the first subshell in S, there's only one value, a 0 value, for orientation. So there's only one orientation of the S, so this becomes an S orbital. Only one way to position a sphere in three-dimensional space. Then if we look at N equals 2, on N equals 2, this is the second shell, or the second ring. It's bigger. And as we can see, think back to the apartment analogy, it's not big enough for two subshells. So 0 stands for the S, and 1 stands for the P subshell. And then down here, when we have 0 for M, that is going to, well, for the S subshell, when M equals 0, that just tells us once again there's just the single one, the S orbital. Now what this M information for the P subshell says is that there's 3 different ways. 1, 2, 3 different ways to orient the P's. And we've already talked about how that's along the x-axis, the y-axis, and the z-axis. So we get 3 orbitals, the px, the p sub y, and the p sub z orbitals. Again, 3 quantum numbers, N, L, M, gives us enough information to define orbitals. So for fun, let's take a quick peek at the N equals 3, the third ring. Okay? If N equals 3, L can be 0, L can be 1, L can be 2. 2 is N minus 1, so we have to stop there. There's only 3 subshells. Remember, the number of subshells, 1, 2, and 3, is always equal or the same number as the level, the floor you're on. Okay, so this is S sublevel, this is P, and this is D. Now, for each of these L's, we have some M values. So if L equals 0, M can only be 0, and this is, again, the S orbital. If L equals 1, then M sub L can be -1, 0, or +1. Those are Px, Py, and the Pz orbitals in the P subshell. When L equals 2, we can have even more M values. We can have -2, -1, 0, +1, and +2. So this tells me that there are 5 orientations for the D sublevel. And those orientations, like I showed you earlier, are the dxy, the dxz, the dyz, the dx squared minus y squared, and the dz squared. So the logical question you're going to have for me is, how do you know which one goes where? And my answer to you is that there really is an indication. One of them really does go, like for example, dxy really does correspond to one of these, and it's not random. But the math behind this is so much more advanced than what we're ready to do in high school that we're going to say for right now it's not that important. All you know is that there are 5 possibilities, and here they are. Okay, I'm going to do one more. I'm going to guide you through this one, and I want to see if you got it. So give it an effort. Let's start with N equals 4. Hit pause and tell me all of the L values that you have. Go. Alright, you should have come up with L equals 0, L equals 1, L equals 2, and L equals 3. Okay, now that you've got that, hit pause and tell me what your M values are for each one of these L's. Hit pause and go. Alright, you should have gotten M equals 0 here. For L equals 1, M equals -1, 0, +1. For L equals 2, your M values are -2, -1, 0, +1, +2. And finally, when L equals 3, M is -3, -2, -1, 0, +1, 2, and 3. Again, first ring, 1 subshell, 1 orbital. The second ring, there's 2 subshells. 4 total orbitals, 8 total electrons. And then it gets so much bigger, by the time we get to where there are d orbitals, there's 5 of them. By the time we get to the f orbitals, there are 7 of them. And I bet you can guess how many g's there would be. That's right, there would be 9 g orbitals if we were to go that far. Okay, hope this helps. We'll do some practice in class. Come see me if you need any more help.